Hello, Deidre, can you hear us?
Hi, Tusang. Yes, I can. How are you?
Doing well, thanks.
And that's good.
Yes, everybody's here. All the presenters are here. We just tested the presentations and the videos and everything is working.
Okay, perfect. Great. I think let's give it another minute. I see the delegates are busy joining,
Hmm.
and then we can start.
Yes, of course.
All right, great. Thanks, Tusang.
No worries.
Okay, Tusang, I think I'm going to start. All right. Perfect. Good morning, all delegates, or good afternoon, at least. I'm still stuck in the morning. Once again, thank you for joining us on our second sessions of the workshop at Sabia. And in this session, we'll be covering biogas plant designs and operations. Just a couple of, or just some information. We have the chat open on Teams. Tusang will take notes and note all the questions that's being asked. We will then obviously send the presentations of today's session as well as the recording to all the delegates that are participating in session 2. We are extremely privileged to have 3 speakers today. Each of them have been allocated a time period to their presentations, and that leaves us some time at the end of this workshop session to answer the Q&As that has been posted on the chats, and then we can get some answers from our speakers. I'm gonna go ahead and introduce our speakers. Our first and second speaker, Dr. Christopher Eden and Dr. Jurgen Thiel. Dr. Eden currently serves as the CEO of Organics Hespros, a subsidiary of Organics based in Spain. His responsibility encompasses the Iberian Peninsula and Spanish-speaking regions worldwide, while also being involved in marketing and communications across the company. Dr. Eden has 25 years of experience in solar PV, landfill gas and biogas utilization projects. After an early career working with leading landfill gas operations in the UK, Chris spent 12 years as CEO with the Spanish renewable energy group Energia, focused on the degasification and generation of power from landfill sites, including a 24 megawatts of landfill project in Spain and 11 megawatts in Portugal. Chris is a director of several environmental engineering companies and is currently developing a major landfill gas IPP project in Morocco. Welcome, Dr. Christopher Eden. Then our second speaker is Dr. Jurgen Thiel. Working alongside Dr. Eden, Dr. Thiel has over 46 years of experience in biogas systems advisory services and has focused on applying biochemical engineering principles and a detailed understanding of the key microorganisms involved in biogas production, their requirements, and their optimum use. His work involves the identification of attractive commercial opportunities for optimizing biogas plant feedstocks and making site-specific system choices suitable for improving biogas production yield while avoiding costly errors. Jurgen's advice is frequently sought after by key clients in municipal wastewater treatment plants, operations, and various industrial sites, including palm oil, milk, sought after by municipal wastewater treatment plants, operations, and various industrial sites, including palm oil, milk, cheese, red meat, poultry, vegetable, and starch and sugar processing facilities. As a member of the organics team, Jurgens contributes to the biogas project cycle at various stages, including inception, process concept design, commissioning, planning, and client care. Our third speaker, we also say welcome to Dr. Patrick Mukumba. Dr. Mukumba is a senior lecturer of the physics at the University of Fort Hare. He has a Master's of Science degree in renewable energy and a PhD in physics, renewable energy. He is a specialist in renewable energy technologies, including biomass, which includes biogas technology, pyrolysis and gasification, wind energy, solar thermal collectors, photovoltaic modules, hydropower plants, and storage components, which includes batteries and fuel cells. He has published more than 30 papers in accredited journals. He has also contributed to research in topics biogas and anaerobic digestion. He supervises master's and PhD students and is also an NRF-rated researcher. We welcome all three of our speakers and thank you once again for presenting at session 2. And I hope the delegates can obtain as much information as possible from our speakers during this session. Then I'm going to give the floor over to Dr. Christopher and Dr. Jurgen. Welcome and thank you. And the floor is yours.
Okay, good morning, good afternoon, everybody. My name is Chris Eden. We're going to be presenting doing our presentation via video. It seems to be causing less technical problems, so I should share my screen with a bit of luck. Can everybody see that now? Is that?
Yes,
can you
we
see
can
that?
see.
Yes.
Yes,
Okay.
Yes,
So
that's
here we
clear.
go, everybody. Thank you very much. Good afternoon, everyone. My name's Chris Eden. I'm a director of the Organics Group of Companies based in Spain. I'll be making a presentation together with my colleague in New Zealand, Jurgen Thiel. And today we'll provide some insights about the anaerobic digestion of organic waste. We'll look at the technology used in the industry, this with particular regard to its value in producing biogas as a commercially viable source of renewable energy. The purpose of this presentation is to raise awareness about the challenges faced by the waste management industry and to look at anaerobic digestion as a potential solution for the treatment of organic waste and wastewater. We'll start by touching on the growing problem of waste generation worldwide and its environmental, social, and economic impacts. We'll have a brief look at how AD works and then discuss the various techniques used in anaerobic digestion, including the different reactor types, operating conditions, and feedstock options. Throughout the presentation, we'll provide you with several examples of the technology. Before I start, though, a word about our company, Organics. We've been involved in environmental engineering since 1985, a trajectory that's touched on most aspects of landfill engineering, with particular emphasis on the control and use of biogas. This includes not only anaerobic digestion of organic material, but also in using landfill sites as the principal anaerobic digester for the generation and storage of biogas, as well as the production of renewable energy. Latterly, we've been involved in the installation of equipment for anaerobic digestion and the fabrication of equipment for the production of biochar, especially from organic materials, including digestate from the anaerobic digestion process. The world is facing a growing waste management crisis that affects every country and everybody. The situation is well presented in this brochure prepared by the World Bank. As urbanization, economic development, and population growth continue, the World Bank projects a staggering 70% increase in global waste generation, from 2.01 billion tons in 2016 to 3.4 billion tons by 2050. Food and green waste make up a significant proportion of the total waste generated globally, accounting for up to 40%. While Africa currently generates the least amount of waste compared to other regions, it still faces unique challenges in terms of modernizing and improving its waste management practices. Shockingly, At least 1/3 of this waste is currently mismanaged through unsustainable practices like open dumping or burning, leading to environmental, health, and economic consequences. This alarming situation underscores the urgent need for effective and sustainable waste management solutions to protect our planet and its inhabitants for generations to come. Moreover, the inefficient use of resources and the failure to recover valuable materials from waste streams leads to significant economic loss, not to mention the missed opportunities for job creation. So something needs to be done. Recently, anaerobic digestion has become de rigueur for the treatment of organic waste. Anaerobic digestion is a sustainable waste and wastewater treatment solution that breaks down organic matter in the absence of oxygen, reducing pollutants and pathogens. This process yields biogas, a renewable energy source, and provides multiple benefits such as nutrient recycling and economic advantages. As shown in this diagram, anaerobic digestion is a biological process that occurs in the absence of oxygen, where microorganisms break down the organic matter into biogas and digestate. The feedstocks from AD can come from a variety of sources, including manure from livestock, wastewater with biosolids from municipal sewage sludge, as well as other organic waste such as fats, oils, grease, and crop residues. These feedstocks can be digested in isolation or co-digested to optimize the AD process. During the process, the feedstocks are broken down by the microorganisms in an anaerobic environment, typically within a sealed reactor or digester. And the end products of this process are biogas and digestate. Biogas is a renewable energy source composed primarily of methane and carbon dioxide, which can be used as a renewable fuel, while digestate is a nutrient-rich source that can be used as an organic fertilizer or soil amendment. The diagram also highlights the potential of using biogas to power the AD process itself. In this next diagram, we show the different types of technologies that are used in anaerobic digestion. Each of these processes has its pros and cons, and each can be suitable for any given situation with regards to how the feedstock material is collected and fed into the system. We'll look at the following techniques. Firstly, the covered lagoon anaerobic reactor. Secondly, the continuously stirred tank reactor, the most commonly used technology for AD projects. Thirdly, the temperature phased anaerobic digester, which is a variation on the last technology. And finally, the dry cell anaerobic digester. We won't be dealing with the other items listed on the diagram, other than to mention that these are techniques for conditioning biogas before it can be used. Once it's been cleaned and prepared, biogas can be used to generate electricity or heat, and used as a vehicle fuel in the form of compressed biomethane. So the first technique we're going to be looking at is the covered lagoon anaerobic reactor. It's a process that treats liquid waste with low solid content in large, shallow earthen basins covered with a gas-tight membrane. The anaerobic microorganisms break down the organic matter, producing biogas and treated effluent. The process is suitable for waste such as animal manure, industrial wastewater, and diluted food processing waste with a solid content of less than 3%. Lagoons are designed to have a depth of between 4 to 6 meters and a large surface area with a retention time of around 30 to 60 days. Biogas yield depends on the feedstock type, the organic loading rate, and the operating conditions, while the treated effluent can be used as a fertilizer. This photograph shows a covered lagoon installed on a palm oil wastewater treatment plant in Indonesia. The lagoon is purpose-built with a series of internal injectors that encourage methane production. The biogas generated must be cleaned of impurities before it can be used. Operating parameters include that it can operate between 10 to 40 degrees centigrade, depending on the climate and the availability of heat. But of course, this has a direct effect on the retention time, which can be between 30 and 60 days, depending on the feedstock and the temperature. The pH is maintained between 6.5 and 7.5 for optimal microbial activity. After the biogas has been generated, it must be prepared for use. And this includes stripping the biogas of impurities, one of which is hydrogen sulfide, which can be particularly corrosive to mechanical equipment. This photograph shows the biological hydrogen sulfide stripping system used on a palm oil mill effluent lagoon. In the next photo, this illustrates the use of biogas from the digestion of palm oil mill effluent. In this case, the methane is being used for the generation of power to provide electricity to the palm oil mill itself. I'm now going to hand you over to Jurgen Thiel to discuss the thermally phased anaerobic digestion technique.
The continuously stirred tank reactor digester, or CSTR digester, is a workhorse of the global anaerobic digestion industry since decades. Modern versions have cylindrical or egg-shaped tanks with a synthetic double membrane roof for biogas storage. CSTR is a type of anaerobic digestion where the feedstock is continuously mixed in a cylindrical egg-shaped reactor tank. Bacteria break down organic matter in the absence of oxygen, suitable for liquid feedstock with a solid content of up to 12%. For example, wastewater treatment plant biosolids or industrial wastewater. As minimum solids content, we recommend 0.2 to 0.5% solids content and a minimum COD of about 3,000 milligrams per liter. Feedstock should be free of large particles and grit to prevent sedimentation. Myself, as an anaerobic digestion advisor for over 40 years, I have basically extensive experience with many different designs of CSTR digesters, many different mixing systems, and we will discuss some of that here in this presentation. Here is a schematic basically showing that for a manure application, the feedstock will be pumped into the digester either at the bottom or the top, as shown here, and the mixing system that can be mechanical or hydraulic with jet mixing, or where biogas recirculation through the tank with the aid of eductor tubes brings the feedstock in contact with the resident sludge of the anaerobic bacteria. Feedstock should be free of large particles. This is a design from 1990, one of the first agricultural digesters in New Zealand, working on the sheepyard droppings as well as high-fat waste from the rendering operation at a large slaughter facility. In the old days, the biogas was stored in an external pillow tank. Normally, these days, we have it all under the roof in the double membrane roof. Here, a more modern application with a fixed roof CSTR digester from the largest food waste digester in the Southern Hemisphere that was designed and constructed in 2000 in Sydney. And the biogas was basically used as it was generated for power production and for drying the digested residue. At Organics, we offer, in addition to traditional CSTR design, CSTR Plus, where we add features to increase the digestion efficiency and the organic loading rate. Mixing systems like mechanical, gas injection, or pump recirculation are available for all those applications. Temperatures could be mesophilic or thermophilic, maintained by external heat exchangers or internal heating coils. Solids residence times, depending on the concentration of the feedstock, between 10 to 40 days. And of course, temperature plays an important role. And a standard CSTR without the plus feature may be 2 to 5 kilograms COD per cubic meter digested per day, a suitable organic loading rate. With the plus feature implemented, it is typically double that amount. It could be triple depending on the nature of the waste. Critical is, as always, balancing the biogas production and process stability. Here, an example from New Zealand where the plus feature, a recuperative thickener, is basically housed in a container that is connected up to an existing 50-year-old digester tank, which allowed to double the throughput and the COD loading rate, the permissible COD loading rate, to this already existing digester tank. So it can be retrofitted. The feature is basically shown with this process flow scheme in the red arrows, that digester contents are continuously pumped through the thickener. The thickened sludge is returned into the digester, and the excess filtrate that has been removed can be disposed to further treatment or other applications. And the thickened sludge, part of it can be also forwarded to sludge dewatering to make sludge cake for export from the plant. Typical thickeners can be drum thickeners, but there are many other options that we can choose from. All have in common low power consumption, fully automated, low maintenance. A weekly clean is normally sufficient, and low polymer consumptions, 4 to 5 kg polymer per ton dry solids. For example, in dewatering, the polymer dose will be 2 to 3 times that amount. Here, a example of the filtrate removed from a municipal wastewater treatment digester. And in this application, the recuperative thickener was here in a separate building and allowed basically to run the whole sludge load in a single tank, permitting the clean out and rebuilding and optimization of digestion in the other tank. And then one could basically swap over the thickener to the reconfigured tank and also upgrade the tank that was before running at double the load due to the recuperative thickening or the plus configuration. In high fat content waste applications, the plus feature is possible, but typically would not be as advantageous as in standard CSTR applications. Continuous mixing prevents formation of dead zones. The biogas yield depends on feedstock type, organic loading rate, and operating conditions. Typical biogas composition could be 55 to 75% methane. High fat content gives high methane content in the biogas. And we use a bioengineering approach to optimize the digester bacteria culture for fat digestion. This is an application of a CSDR plus feature in a recent dairy factory commissioned by us 5 years ago for the removal of DAF sludge and other high fat wastes from the dairy factory. Now, the big picture that this is based on is the standard known flow diagram of carbon and electrons in anaerobic digestion. Complex organic polymers are converted to volatile fatty acids, long-chain fatty acids. They are broken down by symbiotic bacteria into acetic acid, hydrogen, and formic acid. And then hydrogen and formic acid and acetic acid are removed from the digestion broth by methane bacteria to produce CH4 and CO2. So methane bacteria remove acid in essence and produce gas, therefore leading to acid removal and neutralization of the pH in the digester. If the flow from the top into the digester is higher, then the removal activity the methane bacteria can catalyze, the digestion process is likely to acidify and basically self-inhibited. Other inhibitions are ammonia. Ammonia is produced from the protein degradation, and ammonia nitrogen is also gradually inhibiting methanogenesis. And long-chain fatty acids from fat degradation are very potent inhibitors of methane bacteria. So the system has to be well balanced to have a stable COD flow from the top to methane and CO2. So if we look at the big picture, then we see that mesophilic ranges have typically half the capacity for COD loading at the top, at the complex hydrolyzing bacteria level, and also half the capacity of the thermophilic bacteria. So mesophilic bacteria, usually half of the capacity of the thermophilic bacteria for methane production and COD removal. In order, therefore, to adjust a digestion process, one can couple two CSTRs in series, have a digestion stage separation, and we'll show an example later on in this presentation. And this digestion stage separation adds robustness and resilience to the digestion process. The initial hydrolysis stage produces acids, and the final methanogenic stage removes the acids in a separate tank. Suitable conditions, I will not discuss this here in detail because we're running out of time. Happy to do it in questioning. I'll document it here in this table, as well as the inhibition thresholds for various process parameters like temperature, pH, sodium, potassium, volatile fatty acids, and COD level in the digester. Again, I would prefer to do that in the questioning rather than in this presentation here now. One application of separating the phases of anaerobic digestion into two sequential CSTR digesters is temperature-phased anaerobic digestion, or TPAD. TPAD, basically dewatered sludge or anything else like municipal solid waste, can be macerated and then pumped into a thermophilic reactor where the hydrolysis happens twice as fast as under mesophilic conditions at 55 to 65 degrees with a solids residence time of 1 to 2 days, turning a proportion of the loaded material into acid. And the acid is then pumped into a methane reactor. And we changed this, that the hydraulic residence time is preferably 8 to 10 days, not 5 days as it was before shown in the diagram. The solids residence time, typically 10 to 15 days in the mesophilic reactor to degrade the products of thermophilic metabolism. The hydrogenized solids of this type 1 temperature-phased anaerobic digestion, temperature-phased because a thermophilic phase is followed by a mesophilic phase. The solids can be removed for dewatering and then composting, and the centrate can be used as feedstock to recover the ammonia in ammonia recovery facilities. This is a typical type 1 TPAD. Type 2 TPADs are slightly different, where we make the first digester much bigger than in type 1 TPADs, getting a long solids residence time in excess of 15 days, and therefore quantitative breakdown of the organic matter under the preferable thermophilic temperature at higher rates, and then pumping that from a type 2 system through the mesophilic reactor, very similar to the mesophilic reactor in a type 1 TPAD system. Here an example of a type 2 TPAD from the wastewater treatment plant in Christchurch, suitable for a wide range of feedstocks. It gives us higher biogas yields because at the high temperature and long residence time in the first thermophilic stage, we're breaking down complex polymers much more extensively than we would do that in a type 1 TPAD. Typical biogas composition, 60 to 70% methane, and ammonia could be recovered, is not recovered in this case, but could be recovered after the first stage because the breakdown of the carbon has been nearly quantitative, and so the protein hydrolysis and breakdown as well. A case study now for this startup of the type 2 TPAD in Christchurch. The first stage, acetogenic thermophilic phase at 50 to 60 degrees. The second stage, methanogenic reactor at 30 to 40 degrees. The first stage had a volume of about 15,000 cubic meters in 2 tanks. The second stage, a volume of about 18,000 cubic meters in 4 tanks. Because of the configuration, we've heard the first stage 15 to 25 days SRT, and therefore a neutral pH. The acid production was handled by thermophilic methane bacteria, and it gave us a much better yield of biogas. And the second stage was basically used to remove any residuals of degradable COD from the effluent from the first stage. So the original digester plant commissioned in 1961 had 4 times mesophilic reactor tanks, and my team was then appointed in 2010 to design the commissioning and startup of the thermophilic stage using mesophilic bacteria as seed sludge. And I'll bring you an example in this case study how that can be done. With the startup regime we designed and implemented, we increased the biogas production by 67%, estimated 70% from the increased solids residence time, and the rest came 30% from an increase of the activity in the thermophilic digester. So it's a combination of beneficial events that gave us the significant increase of biogas production. The volatile solids destruction efficiency increased by 19% to a total efficiency of 77%. And the solids content in the digested solids basically was at slightly less, but at the same time, the volatile solids content of digested solids increased. So decreased, sorry, from 69% to 62%. Evidence that the organic matter has been degraded more quantitatively. Here is the actual profile. The blue bars give us the activity of gas production measured as methane in the mesophilic stage, and the red what was produced in the thermophilic stage. And as you see, this is in 2010, so reported in 2011. Once the thermophilic tanks were operated in mesophilic conditions, the extra working volume they provided allowed a gas production increase from about 450 normal cubic meters per hour to about 650. So simply because of the added working volume. But then once we did changed the operating temperatures and turned the mesophilic sludge through thermophilic acclimatization into thermophilic bacteria, radically the thermophilic bacteria took over the COD flow and turned the total load in about 750 normal cubic meters per hour of methane, of which about 20% came from the mesophilic activity in the second stage, and 80% of that increased gas production came purely by the type 2 cultures that was established in the thermophilic stage. So what it tells us is there are different ways you can do temperature phase digestion. And the way we designed and implemented in Christchurch, we also have implemented at other facilities, gives that at the end of the day better results than a traditional type 1 TPAD design. This type 2 TPAD can also be applied to non-municipal waste. Here, this is a design that Organics is offering for fruit and vegetable waste in various places. This would probably even end up in South Africa if the project is accepted for implementation. We would have a mixed waste with a very low contaminant level that is further decontaminated from plastic and paper and timber residues. Glass and metal would be absent from the waste by default. Those rejects will be removed from the facility after handpicking a trommel screen that removes other materials that would not be picked up by the handpicking. Then a macerator turns it into a small slurry of small particles, and in a deep day tank pH dosing to add alkalinity, we would produce the feedstock for a type 2 thermophilic design. The reactors would be operated under the conditions we discussed before for type 2 applications. Sand and silt would be removed from the bottom and scum from the top, and what's left over after thermophilic treatment then polished in a mesophilic reactor, again with recuperative thickening to increase in a CSTR plus configuration to increase the reaction rate and the efficiency of the mesophilic bacteria. And biogas can then be put to various applications, I say vehicle fuel, etc., etc.
So the final technique we're going to be looking at is the dry cell anaerobic digestion. This is a technique in which organic material is stored in a chamber for enough time to ensure complete digestion of the organic content. The solid content of the feedstock is much higher, generally between 20 to 50%, and the only water that's added is generated by the process itself. Digestion takes place in a sealed, oxygen-free reactor where microorganisms break down the organic matter, producing biogas and digestate. Dry cell requires less water and smaller reactor volumes, reducing the overall footprint of the digestion plant, and it can handle a wider range of solid feedstocks, including those not suitable for wet digestion. There are two types of dry cell anaerobic digestion. The diagram shows a garage-type reactor in which the feedstock is loaded and unloaded using front-end loaders. The biogas yield is typically between 50 and 60% methane, with up to 40% carbon dioxide, and the feedstock is left in place for around about 30 days. The second type is a plug-flow cell reactor. These are used primarily at dairy operations where manure is collected by scraping and then moves through the reactor as a plug. Using this technique, there is usually minimal mixing. Biogas yields are similar to the garage-type reactor, and in both cases, digestate from the processes can be used as a fertilizer or soil conditioner. But generally, this requires further processing, such as composting or drying, depending on how it's going to be used. The images are from a project that we installed in Bali, Indonesia. The plant was a dry cell plant treating municipal solid waste. As a first step, the feedstock had to be separated using a series of trommels. The organic fraction was then fed into a series of dry cell digesters, and in this case, garage-type digesters, and it was left there for around about 30 days. The produced biogas was cleaned of impurities and then used in the generation of power. In this case, the energy was used on-site as well as being injected into the national power grid. So in conclusion, we can say that anaerobic digestion is a versatile, proven, and sustainable technology for biogas production, and is an appropriate technology for dealing with vast amounts of organic matter that are being generated and are projected to be generated in the future. We've covered several techniques, including the ones listed here, and in particular, we can say that its value lies in, firstly, the production of biogas, which is a versatile renewable energy, and in reducing the dependence on fossil fuels, as well as mitigating the greenhouse effect. It reduces the volume of waste that goes to landfill and the problems associated with odor. It produces a nutrient-rich digestate and supports local economies through job creation.
Thank you, Dr. Jurgen and Dr. Thiel, for the very informative presentation that you have presented to us. We have one question that we will direct to you at the end of the session in our Q&A session. Just a reminder, and Susan has posted it in the chat group as well. If you have any questions, please post it in the chat, and then we can present it to our presenters at the end of this session. Once again, thank you, Dr. Jurgen and Dr. Thiel. Much appreciated. Now we're going to hand over to Dr. Patrick Mukumba. Patrick, the floor is yours. Thank you very much.
Good afternoon, colleagues.
Good afternoon, Patrick.
Good afternoon, Doctor.
My presentation is based on biogas plant design and operation. I will start with the introduction and followed by design principles and considerations for biogas plants and key components and equipment used in biogas digesters, operating and maintenance practice to optimize biogas production, troubleshooting, and I'll give a conclusion and references. Currently, we're working on small-scale biogas digesters. And with the term, we'll work on digesters at activated sewage treatment plants, that is large-scale digester systems. So on my slide, the first digester is an underground digester. We're working with those ones, and also we are designing portable biogas digesters, like the one that is shown there. And the third digester, we're also designing these digesters, surface digesters that are sawdust insulated, because you find that now, if you just put a digester in the built on the surface, we have got a challenge of temperature fluctuations. Therefore, we need to insulate our digesters. So you can find that the digester is a surface digester that is insulated with sawdust to minimize temperature fluctuations. And the fourth digester, these are balloon digesters, and they're very common in many communities. And the fifth digester, it's a solar-assisted biogas digester with a green or with a green envelope. And the fifth digester, the sixth digester, is a chromatic digester, and this is very common because they can suit to African climate. And the seventh digester, it's an activated digester, a large-scale digester, and with time we're going to work on these digesters. On design principles on digesters, for example, if we are given a situation whereby a farmer has got a number of animals, it can be goats, it can be cows, it can be sheep, you are supposed to know the design considerations, what is expected, and how is the digester going to be built, and the availability of substrate. So when designing a digester, the following should be considered. We consider feedstock characteristics, or what type of feedstock are you going to use? It's like if a farmer has got cows, how are you going to design the digester? If you have sheep, how are you going to design the digester? So meaning that on our design equations, you find that there is an equation that involves use of, or the quantity of the substrate, or the quantity of the waste to be used for biogas production. So you have to consider feedstock, or you have to consider quantity and the quality of waste. For example, if you're using cow dung, you can say that cow dung has got less biogas as compared to human waste. And cow dung has got less biogas as compared to poultry manure. And also, when you are designing these systems, you are supposed to consider pre-treatment requirements. You can find that some waste they require before they are fed into the digester. Like when you are using poultry manure. And also, when I'm designing these digesters, you have to consider the time taken. The waste is going to be in a digester. For example, if you're using grass as a feedstock, you want to produce biogas from a vegetable material, from grass, from leaves. You can find that the retention period for those leaves to be in the digester is much longer as compared to cow dung. So therefore now, when you are feeding those wastes, you have to consider the inoculums, or which seeds are you supposed to use to catalyze the process so that biogas production can start even on day 5 or on day 10. So you have to consider time taken, these hydraulic and organic loading rates. And also when I design systems, you have also to consider gas collection and storage. Your system should be airtight, because you find that in most cases, most road digesters, there is a problem of leakages. Biogas is produced, but on the way now, it can leak. So therefore, we have to consider a gas tightness so that there are no gas losses. And also, when I'm designing these systems, you are supposed to consider storage capacity. How are you going to store your gas? Because, for example, you are producing large amounts of gas, and you find that now you don't have gadgets to utilize the gas. So meaning that you need to have even biobags to store the biogas, or you can have these LPG cylinders, whereby if the gas is compressed, then it is stored in LPG cylinders. And also, in your design, you should consider whether the biogas is going to be purified. For example, you want to use the biogas for driving a petrol engine. For example, you've got old petrol engines, and you find that sometimes petrol may be very expensive. So now you want to use biogas instead of petrol. So meaning that now that biogas need to be purified, because like carbon dioxide, if you just feed biogas with carbon dioxide in the engine, carbon dioxide is incompressible. So meaning that carbon dioxide is being removed, so that when biogas is used as an internal combustion fuel, it can burn, because carbon dioxide, which is incompressible, has been removed. And also, we have got different designs of biogas digesters. So you can find that now we have got fixed dome designs, floating designs, and so on and so on. And also, when I design these systems, as I've said, you are supposed to consider a retention period. Like some wastes, they need more time to be in the digester, and sometimes some wastes, they need less time. And also, we should consider even temperature. You find that now, like in most road digesters, digesters are built underground, because underground digesters, they're not affected, or they are affected minimally or by temperature. Because when there are temperature fluctuations, you find that now biogas production is affected. So meaning that in this case now, let's say in cold regions, we can introduce some renewables to ensure that biogas is produced at a constant temperature. For example, you can produce biogas at 35 degrees. How are you going to produce biogas at 35 degrees? It means that you can just even incorporate a solar module supplying electricity to a battery. But before you do that, you have to size the battery, you have to, according to the coil that is going to heat the waste in the digester, because you want to produce biogas at a constant temperature. Because when there are temperature fluctuations now, it means that biogas production is affected. Or you want to heat that coil by electricity. You can have a turbine, just a small wind turbine, like a 1 kilowatt turbine, which can supply electricity to the battery. And now the battery can supply constant DC current to the coil that is supplying heat. But now there's a lot of alternatives that can be done to ensure that now, what about when temperature falls, let's say below 35 degrees, what happens? When temperature is above 35, assuming that now, but you can just power our battery using some renewable, whether it's wind turbine, you can have a wind turbine, we can have even solar modules supplying electrical energy to the battery, but you have to size these systems. And also, we have to consider pressure, because sometimes now, we're not designing our systems, you have to consider pressure, because a lot of pressure can accumulate in the digester. So we need to have some valves. So when there is a lot of pressure now, then you can open the valves to ensure that now our system gets burst because of too much pressure. A number of digesters, they cracked because of too much pressure within the digester. And also ventilation. It's, for example, when you're putting your system, you find that now, like you're using cow dung, you find that some wastes, they can pollute the environment. So you need an environment now where there is a lot of ventilation. And also, we have to consider waste management and environmental impact. Digested management. How are you going to manage the slurry or the digested? Are you going to use the digested or the slurry as a fertilizer? Are you going to fertilize your crops? So all these things are considered, and the stability and the flexibility. Also, these factors are also considered when we are designing our digesters. And also, economic and financial considerations. When it's, for example, a farmer, you can say, okay, I've got 100 pigs, 100 goats, 100 chicken, 100 even sheep or donkeys. When you are designing the system, we have to consider economic and financial considerations. It's, for example, you design your system, you have to consider profitability. You are designing that system or the digester for producing electricity, and you have to produce electricity economically. So meaning that now you have to calculate, when you're designing the system, we have to calculate the profitability. How much profit is supposed to be obtained by the farmer? Because you cannot just have that system for zero profit. And also, when you're designing a system under economic considerations, you are supposed, if the farmer, let's say, he wants to get money from the bank, you have to tell the farmer, this is the payback period, and this is your profit. This is the net present value. This is the internal rate of return. Because the farmer needs to know all those things, because he should not produce electricity, not economically, because he's supposed to even sell the biogas, even to neighbor communities. He's supposed to sell the biogas in form of compressed gas, because he can just produce biogas, he can purify it, then he can compress it, and he can store it in cylinders. He can sell all those the biogas in cylinders, assuming that he has to produce electricity economically. Or we can take the biogas, and the biogas now, which is not purified, we can feed it into the biogas engine, biogas generator, and we can get electricity straight, even before purification. And also, you have to consider revenues. and I've mentioned this, because you are producing biogas. When I'm producing biogas, you can just have even the digestate. You can sell the digestate or the slurry to nearby farmers, because the digestate is more nutritious than the influent. If you take cow dung and sell cow dung to a farmer, and you sell the digestate or the slurry or the effluent from cow dung, you can find that the effluent from cow dung is more nutritious. And also, when we are designing our systems, we are supposed to consider regulatory and the social considerations. And these ones are highlighted. And also, they embrace community impact. What is the impact of installing some digesters in a community? Are you producing electricity from the biogas? Are you doing engine modification because of the biogas? Are using the biogas for heating purposes, and so on and so on. So you have to consider this, because the community is supposed to benefit from the biogas projects. And monitoring and the control systems. So meaning that now, when we are on our design, we have to consider how we are going to monitor the system. And this system should be automated. It's, for example, you want to measure biogas production. You cannot just come with an instrument and measure biogas production, and then you go back. So we need automated system. You just put your biogas analyzer there, and you can just go anywhere. So the biogas analyzer has to measure biogas production hourly, daily. So you can come after even 1 month, and you just take your results. So on day 1, the biogas production was like this. On day 2, it was like that. On day 3, it was like this. If it is pH, because pH is very important on biogas production, and it should be controlled. So you need to have pH meters that are data-logged. pH meter, it can measure pH like 10 o'clock in the morning, then 11 o'clock. So you can find that all the information that is being measured, it can be stored. So after 1 month, you can just come and you can just download, and you can see that, okay, on such a day when I was absent, okay, the digester pH was like this. Right. So you can find that now. I found it necessary to have some design equations. You can find that now. A farmer can come to your home, and you can say, okay, I have got so many pigs, so many horses, so many donkeys, 100 vegetable beds. I've got a lot of leaves. So I want to have a digester at my farm. So and the farmer can say, I want 5 cubic of biogas to be produced daily. He can just say, no, I want so much gas to be produced daily. So we can design the digester according to the requirements of the farmer. Because the farmer is saying, I want 5 cubic of biogas to be produced daily, because my gadgets, my engines, my generator, and all the gadgets that they have, they need 5 cubic of biogas a day. So we are designing according to the requirements of the farm. So meaning that now, first of all, you are supposed to come up with an equation. So an equation that you can use here, we're saying that now, a biogas production daily is given by GP is equal to W times 0.036. In this case, we're saying that now, the farmer is saying, I need 5 cubic of biogas daily. Then where the GP, we put 5 cubic meter of biogas daily. And there, you find that now 0.38 from our calculations, from our biomass resource assessment, because sometimes you want to know in a particular location the amount of biogas produced from cow dung or from donkey dung. So meaning that now, as from our experiments, 1 kg of cow dung produces biogas of 36 liters. In cubic meters, it is 0.036. So meaning that now, in that case, you want to design a digester for the farmer. Because let's say the farmer has got so many cows, but now what is limiting us? The farmer is saying, I need 5 cubic meters of biogas. So we're designing according to his requirements. So now you can find that now. This is why we have said we're not designing now, we are considering the waste that are available. So you can say that W is standing for the weight of the feedstock. But this weight of the feedstock, it's before we mix it with water. It's like you take fresh cow dung. You cannot take fresh cow dung and feed it into a digester, because we have to measure total solids and volatile solids. We measure volatile solids in order to find how much water are we supposed to add to fresh cow dung. And usually it's 1:1. 1:1. So you can find that now there we're trying to this is an equation that is used to find the volume of the digester. We want to tell the farmer, your digester is at this volume. You want to produce so much gas. So for you to produce so much gas, you need a digester with this volume, with this diameter, with this height. Second point, we can come to a farmer, and this farmer can say, okay, I have got like a farmer, he has got 20 head of stabled milk cows, 100 head of pastured cattle, 10 heads of pastured goats. The farmer wants to construct a biogas plant. Here, we want to design the digester according to the waste the farmer has. It's like we are saying, okay, we are 3 in a family. We see now, I just go to, let's say, to a family. Then the family can say, okay, we are only 3 in a family. So we are producing so much waste. So we can design a digester that is proportional to the waste coming from 3 people, whether it's father, mother, and let's say their son aged even 15 years. So meaning that now, the question now, the farmer now, he has got, say, I've got this, but now I want to produce biogas for electricity production. I want to produce biogas. I have got more than 10 engines there. And you see now they are 50 years old, but I want just to drive these engines using biogas. So what should I do? Then now, first of all, you have to calculate the digester volume for the farmer. See, this is the volume of the digester. And now we also calculate from his animals the biogas he can get, because you know that in simple words, 1 cubic meter of biogas, he has got an energy value or an electricity value of 6 kilowatt hours. So the farmer has to know that, okay, if we produce 100 cubic meter of biogas, you convert that one now, because they're saying 1 cubic meter of biogas, he has got electricity equivalence of 6 kilowatt hours. Then you convert that one now. But now you tell the farmer now, if you've got a generator is not 100% efficient now. So instead of getting 6 kilowatt hours of electricity now, then now you tell the generator that from 1 cubic meter now, because you're using an engine which is 40% efficient or 60% efficient. Therefore, now, from 1 cubic meter of biogas, you're going to produce, if it can be 3 cubic, because we're looking at the engine now, right? So meaning that now, calculate the farmer now, so meaning that I've tried to work the digester volume from the farmer availability, or from the farmer's waste. He's got all those animals. So first of all, you are calculating the volume of the digester now. You can calculate the volume of the digester now, and we're saying the volume of the digester is given by SD times RT. This is why you've said that now. When you're calculating the volume of the digester, when you're designing these systems, you need to know the retention time, the time taken by the substrate to be in the digester. And also, so volume of the digester given by SD, whereby SD it's biomass, which can be our waste, plus water, because you have to mix biomass with water. You have to mix your substance with water, whether it's 1:2 or 1:1, depending whether the biomass is wet or dry. So you can find that now here. So you can find that I was trying to work out the equation, see now, and you can find that now. Since now it's goats and the cows. So you can see that now. We have to calculate the digester volume for goats, digester volume for cows, and then what? We just add to find the total biogas digester volume. But however, the farmer may have caged the chicken, and the farmer may have chickens that roam around. So you can find that we're not calculating biogas yield now. You see now, you cannot say that now. The farmer can collect all the waste from roaming chicken, but it's different from caged chicken. So you should consider all those things, whether the chickens are roaming, whether the cows are stilled, or they're moving around. So meaning that now, we can calculate the gas yield using the values for volatile solids. Okay, the second part is the key components and equipment used in biogas digesters. So you can find that since we have said we're designing portable biogas digesters, you can see that now. The components that are quite clear. You see now, we have got intake tank, we have got outlet tank, we have got the active slurry tank, and the biogas tank there, and you have got your biogas tube or biogas from the digester, because this is the digester, and you can find that now here. This, if you want, let's say you want to produce biogas for driving petrol diesel engines, so meaning that now you have to purify that one. You have to remove carbon dioxide, and we have different methods, and this has been outlined to know, okay, like you want to produce we want to remove carbon dioxide from biogas, what is supposed to be done. But this one now, it depends now whether you want to use biogas for driving even petrol or diesel engines. But for powering a generator, you can just have what, your generator somewhere here, and then you can just power it, depending on the methane content in biogas. As long as if the methane content is 60%, then you can just drive your biogas engine. But in most cases now, we need to purify, we need to remove hydrogen sulfide, which can corrode engine parts. Okay, so since we're saying key components and equipment used, you have said now, you have said inlet, outlet, we also need a gas holder, a agitator or a mixer, and it has been mentioned now, because you find that now, those wastes you put in a digester, they are supposed to be steered to avoid formation of scum. So meaning that now you can also design an agitator. It can be an automatic agitator to say, okay, after 10 minutes or after 1 hour, the system, the agitator can steer the digester contents. After 1 hour, it starts to what? It starts to steer and so on and so on. And also, we're not developing these portable biogas digesters because most of them they're supposed to be surface digesters. We should usually include a heating system because you said that there are a lot of temperature fluctuations, like in winter. You find that now in the morning the temperature can be at 20 degrees. In the afternoon, it can be 10 degrees. You can find that those temperature fluctuations, they affect the biogas production. So meaning that now we are supposed to include a heating system, whether you can use a solar water heater supplying hot water to the coils embedded in the digester waste, or you put a solar module and you are supplying electricity to a battery, and that battery supplies electricity to the coil, because usually the coil that we're using is 350 watt coils. So meaning that if you know the wattage of the coil, you're able to size the battery, you're able to size the solar modules, you're able to size, if you want to use a wind turbine, you can size the wind turbine to know, okay, I need a wind turbine of this size, whether it can be even a 100 watt wind turbine or 1 kilowatt turbine, depending on the demand of the coil. And also, we have talked about key components, feedstock, like you want to feed your digester with vegetable waste. Before you feed your digester, you should have shredder to grind the vegetable material or food waste. And also you have to consider a effluent treatment system. And also, as I've said, key components. Also have to consider gas scraping and the purification system. It depends on the usage of biogas. You want to use the biogas for electricity production. You want to use the biogas to drive an engine. You want to use the biogas for heating purposes. You want to use the biogas for cooking purposes. So you have to consider all these so that you know that at the end, if I want to use the biogas for electricity production, should I remove carbon dioxide? Should I remove hydrogen sulfide? Should I remove hydrogen? Should I remove moisture? All those are considered. That's why your biogas system should have a purification system or and an upgrading system. And also gas utilization equipment. Because at the end now, the biogas is supposed to be utilized. You cannot just produce biogas for no reasons. We are producing biogas. I'm producing biogas because I want to use the biogas to drive my refrigerators, to drive my engines and other components in the house. That's why I say you're doing these projects so that there is an economic benefit. And also, on the key components, there should be a monitoring system. This is why we have said that now, on research purposes, we have to put some sensors, some control systems, some data loggers to store the data let's say, this is why I've said you want to measure pH. You don't go to a digester and measure pH daily. You just you need some pH sensors with a data logging system, so that now after, let's say, a retention period, let's say of 30 days or 4 days, then you just take your data logger, then you just download. Then you're able to know that on day 1 there was no biogas production. On day 2, the pH was, you see now, it was like this. On day 4, it was this. And it's also necessary, if you put these systems, you can see that, okay, my digester, the pH is falling, assuming that the digester is now sour. So what should I do to the digester? Then you can put some what? You can even put some wooden ash, or you can just put a lime to ensure that the pH is almost neutral for maximum biogas production. And also gas utilization. Components and equipment used in the biogas digester continued. Here I've given you just the situation that I was explaining. You can have our digester there, and you can find that now. You can have a coil there, and you have got your biomethane that is almost 100% methane. So you can find that now there. We are trying to heat the biogas substrate so that there are no temperature fluctuations. We want to create mesophilic temperature in the digester. It can be between 30 degrees to 37 degrees, because you know that in winter, biogas production is affected. So we need to introduce a heating device to ensure that biogas production is not affected. And also, operating and the maintenance of biogas digesters now, we should consider there should be consistency on how you feed the digester. If you're feeding the digester daily with, let's say, 1 kg cow dung, it should be consistent. And also monitoring and maintaining temperature. You should maintain temperature, because temperature should not fall. If it is at 50 degrees today, then tomorrow it's 10 degrees. You find that now biogas production is affected. So meaning that now you need to control temperature for maximum biogas production, because you want to optimize biogas production. How are you going to optimize biogas production? You want to keep the temperature constant, and also you want to keep pH balance. If pH, let's say, is fluctuating, then you know that there's a problem there. Biogas production is affected. Therefore, we need to put even lime and even put wooden ash. Also, on maintenance, ensure that your digester is always steady. And also, your biogas that is produced is collected, because you cannot just produce biogas and you don't utilize the biogas. And also, there should be slurry removal, because as biogas production is taking place, you find that now you are getting new slurry, or a new digestate, or a new effluent. So meaning that you are supposed to collect the effluent that you can, and you can use this effluent, as you have said, as a fertilizer, or you can sell the effluent. And also structural maintenance, all those factors are considered. And also on the maintenance and operation of these digesters, you should also consider or avoid use of inhibitors. So you can find that sometimes you can just use chemicals, like we can have, let's say, a Blair toilet. Let's say you have a Blair toilet, and you want to produce biogas from those waste in a Blair toilet. So you can find that now, if you just take water with soap and you just pour it in that digester, you can find that, or pour it in that Blair toilet, you can find that there's no biogas production. So meaning that now we have to consider all these factors that affect our biogas production. And also routine maintenance, you have to all the time you check to, okay, what is the pH, what is the temperature, biogas production, the methane content, and you have to check the methane content because biogas is mainly mainly carbon dioxide and methane. So you need to check. This is why you need some biogas analyzers, which can tell you that the amount of methane is so much. And also operator training. Okay, these operators, they need training because if that's not trained now, it means that now digesters can fail. And also troubleshooting common issues in biogas production. You can say that there are a lot of digesters that have been designed and constructed in rural communities. And most of these digesters have failed because of a number of reasons. Right. So, for example, now we can have gas leakages, and gas leakages in digesters that are caused by cracks, by leaks in gas pipes, improper sealing of joints. And how are you going to solve that problem? You should check it regularly. You should check all gas pipes. You should ensure that all joints and the connections are properly sealed. And also excessive scam formation. You can find that sometimes there's a scam and you don't see any biogas production. So meaning that now you should check, okay, the problem is this one now. It means I need to steer my digester. This is say high levels of fibrous and undigested material in the feedstock, inadequate mixing or agitation within the digester. And then now we're saying that now solution pre-treatment. And also ensure that you use agitators or stirrers. And also slurry overflow. Sometimes you can find that the slurry is overflowing. I've seen in a number of digesters. The reasons block the slurry outlets, excessive feeding, and also now solutions now, regular checks, monitor feedstock, because you have to monitor the amount of substrate that you are feeding the digester. That's why you have to calculate the loading rate, how much waste should you load daily or weekly or monthly. And also cracks, you have to check for cracks, poor construction, long-term tears and ways, settling of foundation or ground movement. And you have to inspect digester cracks and repair the cracks. And also, sometimes you can find that now if it is a flowing drum digester, you can find that now the drum is unable to rise. And these are the reasons which are caused. These are the reasons why your drum is failing to rise. And these are the solutions. And also, the drum can corrode, sometimes can corrode. And what causes the drum to corrode? And those are the reasons. And possible solutions, we need to paint the drum regularly and apply anti-corrosive paint. And also, for balloon digesters, you find that now there are a number of issues on balloon digesters. Balloon inflation, insufficient biogas production, balloon material degradation, and affecting elasticity. So you have to address the root causes and also inspect the balloon material, because find that now the material fades with the time. And you find that now pH imbalances in digesters. They can affect, you can see how do you know that the pH imbalances? Accumulation of acids, inadequate buffering capacity, and solution there. Monitor the pH on daily basis. Add buffering agents like lime, sodium, bicarbonate, or just ash, wooden ash. Odor issues, you find that sometimes you go to a digester and around the digester, the place is smelling. Then you start to wonder what is causing all these gas leakages, incomplete digestion. But now the remedy to this, check regularly and repair gas leaks. Ensure there's complete digestion. Install odor control sensors. You can just install a sensor there. This can tell you, okay, there's so much odor coming from the system. And also slow digestion and sludge accumulation. These are caused by low temperature, high levels of inert materials in the feedstock, insufficient microbial activity. And now the solution remedy, insulate the digester to maintain a stable home temperature. This is why on page 2, I've shown you the digesters that were built in on the surface and were insulating these digesters using sawdust. There is plenty of sawdust. So now we are just using the sawdust as an insulating for biogas digesters to ensure that the temperature is constant. And also, conclusion, I've outlined on a type of digesters, design principles, structure, integrity, and viability, balloon digesters, key components, user training, maintenance, troubleshooting. Thank you very much for your attention. And these are some of my references. Thank you.
Thank you so much, Dr. Mukumba, for this very informative presentation. I think we really thoroughly enjoyed it, and I've definitely learned a lot more, and specifically on the designs. Thank you for sharing that knowledge and information with us. We really appreciate it. Delegates, we on to our Q&As. I have seen 1 or 2 questions. Once again, the presentation has been recorded and will be shared to all delegates, as well as the recording and the presentations. We are a bit restricted on time. We've got about 3 to 4 minutes left. If you would like to post more questions on the chat, you're more than welcome to do so. If you want to ask questions on this presentation and the workshop, you're also more welcome to do that. And then we can take it from there. So if you want to ask questions, you all 3 of the speakers are still online, and they'll be happy to answer that. Thank you once again, Dr. Eden, Thiel, and Mukumba, for your presentations. We really do appreciate it. Tusam, over to you.
Yes, thanks, Deidre. So here I see that Pal has asked a question. I'm sorry if I'm not saying your name correctly. So I just unmuted him. So if you would like to say your question out loud, go ahead.
Absolutely. Thank you so much. Yeah, so my question is this. For the processing of pressed sugar cane juice with 18% solids, of which fiber is 7, sugar is 7%, in West Africa plant, it's my understanding from various recommendations that high-rate reactors such as USSB, which are the upflow anaerobic sludge blanket, or ESGB, which are the expanded granular sludge beds, have advantages over the typical lagoon or stirred tank reactors that was, presented earlier today. So I wanted to ask the speakers today, what is possibly your experience or knowledge of these two types of high-rate reactors, which appear to be more economical and effective. And certainly, they need to be custom-made. But the main question is, can you recommend one over the other for this application? And why might that be?
Right. It's Jurgen Thiel here. Can you hear me okay?
Yes, I can.
Okay, thank you for that question. Yes, I haven't spoken about my experience with UASB systems here because we just didn't have the scope to cover it, but they have their advantages for soluble solids. They come originally out of the European Dutch sugar beet industry, which is different from sugarcane juice. And the main complication you find is the fiber that you just mentioned being 7% in your sugarcane juice is actually a complicating parameter for UASB use. Just for everyone, this is a system where the waste enters the bottom of the digester and flows upwards. That's the U, through a settled sludge bed where the particular sludge, the anaerobic bacteria, has to form little pea-like structures or granules so that the soluble waste can percolate between the granules upwards, and the gas as well as the liquid flow keeps that bed settled and moving at the same time. So what you get that way is a concentration of active anaerobic bacteria that is about 4 times as much as you get in a typical CSTR or lagoon reactor. So because the concentration of the bacteria is 4 times higher, of course, the gas production per volume will also be that much higher. However, although this sounds like a very great principle, they do have problems. One is clogging. The other one, I worked with UASB systems myself on pilot scale in the sugarcane industry in Asia. If you have a molasses kind of feedstock, which is not cane juice, but obviously differently prepared with phenolics in it, they can destroy those granules. And then the whole reactor is dead. So I would say there's no general answer. It has to be, as you say correctly in your question, designed for each site based on understanding the actual fluctuations and composition of the sugar-based wastewater. And the construction costs of a UASB will probably be per volume 4 to 5 times the construction cost of a lagoon digester. So although ideally they are doing all right, in particular cases there may be complicating factors in the waste that make it impossible to run a UASB. A good example from Australia. In 2000, we put their CSTR digester in for food waste, and the neighboring property was a yeast factory that used molasses to grow yeast and then processed the wastewater with a UASB. In the processed water from the yeast production were inhibiting substances that made those pea-like structures decompose in the UASB. So those unfortunate owners of a UASB had to buy every year the seed sludge, the pea structure sludge from another factory and transported by rail for 1,000 kilometers. You can imagine the costs. So that's an example where it went wrong. Despite the advantages that it has in principle, it can go wrong as well. It was a long answer, but it gives you sort of a bit of a broad spectrum of applications. where on one end the UASB is a high rate, on the other end the lagoon is a low rate, very robust solution.
Excellent. Yeah, I will leave time for other participants, but thanks for the elaboration. I believe we have your email, so I can reach out for further clarification. Yes?
Absolutely, we're happy to help.
Thank you.
Great. So if anybody else has a question, just put your hand up and I'll make sure to unmute you. No other questions? Okay.
Doesn't look like it to some.
Yeah,
Thank you
no
very
worries.
much.
No worries.
Thank you, participants. And this now brings us to the end of our our second workshop. We will definitely communicate the next or the third workshop and very soon. And thank you so much for your participation. And once again, Dr. Eden, Thiel, and Mukumba, thank you very, very much for sharing your information and knowledge to our delegates. We really do appreciate it. We wish you all a very well day further, if I can put it as such. And thank you once again for participating in our workshop. Have a good day. Thank you, everyone.
Thank you very much.
Thank you. Bye-bye.
Thank you. Bye-bye.
Bye.
Thank you very much. Bye-bye.
Bye-bye.